Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. So in this video, we are going to discuss on tutorial 16. So the topic is polarization. Before you watch this video, make sure you have done the question given in the link provided below in the description part. Okay, the first question. Two pieces of polarizer P and Q are arranged along the same straight line with their axes of polarization, vertical and parallel as shown in the figure. A beam of non-polarized light of intensity I is directed at polarizer P. Polarizer P is rotated through 360 degrees about its axis, but polarizer Q remains fixed. Describe how the intensity I1 of light transmitted through polarizer P changes. Okay, mention here the intensity of light passed through polarizer P and the beam is at incident at P is not polarized. Okay, this is given in the question, a beam of non-polarized light. So the beam is not polarized. So therefore, the intensity is half of the intensity I1 stated here. I1 is half of the initial intensity. So given I, we write as half I, and this I1 I1 equals to half I is constant. Okay, even though the P is being rotated. Okay, next question P. Question B. Sketch a graph to show how the intensity I2 of the light transmitted through polarizer Q varies as polarizer P is being rotated. Okay, so now if polarizer B is being rotated, the intensity I1 here is constant. I1, half I. I1 is constant. So therefore, if this intensity of light half I pass through the second polarizer Q, so it will follow Malus law. Okay, so Malus law is given as I equals to I naught cos squared theta. So that's mean I2 stated here, I2 is the intensity of light after passing through polarizer Q. So I2 is I here is substitute into the Malus law. So this I will be I2 and I naught here will be I1. The light that passed through before the polarizer. So the intensity is given by I1. So the graph is graph of cosine squared. Okay, it is positive because every value that we squared is a positive. So that's why it's a positive. We draw it the positive side, and it's a cosine. And at least you draw a complete one cycle until 360 degrees. And don't forget to mark the amplitude of the graph, which is given as I1, and also the starting point 0. So this is the graph against I2 against angle theta. Okay, next we go to question 2. A beam of non-polarized light of intensity I naught is directed at polarizers P and Q as shown in the figure. The polarizing axes of P and Q are at right angles to each other, okay, given in the diagram here. State in terms of I naught the intensity of light transmitted through polarizer P and then polarizer Q. So the first question, polarizer P. So this is the first polarizer and the light incident is non-polarized. So that's mean the light after pass through the P will become half of the initial. So given here I naught, so that's mean after the P will be half of I naught. So that's the answer. Okay, now the beam continue, or the light continue pass through Q, which is at right angles to P. Q is right angles to P given in the question here. So that's mean using Malus law, okay, I equals to I naught cos squared theta, and the theta here is 90 degrees. and the I node will be half I node. Okay, we substitute into the I node here, and the intensity of light before passing to Q is half I node. Okay, so now we substitute cos 90 degrees. So cos squared 90 degrees is equals to 0. So that's mean the intensity of the light after pass through polarizer Q is 0. Okay, now we go to question B. Keeping the arrangement of polarizers P and Q unchanged. So explain how you would arrange another piece of polarizers R such that the intensity of light transmitted through polarizer Q is different from the answer to A2 above. So we don't want it to be 0. Okay, we want at least the light can pass through the Q. So we add another polarizer in between P and Q. So that's the answer. So we insert the polaroid R between P and Q so that the angle here does not make 90 degrees with the initial, with the polarizer before it, before Q. So we insert R in between, and this R we can incline it at angle to the vertical of P, actually vertical of P. So we can incline the R so that R and Q is no longer 90 degrees to each other. Okay, so as shown in the diagram here, for you all to understand what is meant by insert the polaroid R in between P and Q. Okay, so that's the answer. Okay, now we go to question 3. A beam of non-polarized light passes through two pieces of polarizer. The angle between the polarizing axes of the polarizers is 30 degrees. What percentage of intensity of the light beam, the incident beam is transmitted by the two pieces of polarizer? Okay, so this is polarizer 1 and this is polarizer 2. So the intensity of light transmitted through the first polaroid is half of the initial light, intensity of initial light. So let's say the intensity of the light passing before passing polarizer 1 is I node. So that's mean I1 that pass polarizer 1 will be half of the I node. Okay, so like given here in the diagram. Okay, intensity of the light transmitted through the second polaroid. Okay, we use Malus law. So the light I2, the intensity of light I2 is the light passed through after passing through polarizer 2. Okay, and equals to the I naught is the light intensity of the light before polarizer 2, which is half I naught. Okay, then cos squared theta. Okay, so that's the answer. And then don't forget the angle is given 30 degrees. So we substitute into the equation here. So we get 0.375 I naught. So this is the intensity of the light after passing to polarizer 2. Okay, but the questions one in percentage, in percentage. So this is not in percentage yet. So we calculate the percentage. Continue calculate the percentage. So 0.375 I naught over the original intensity I naught. Okay, times 100. So the percentage is 37.5%. Okay, now we go to question 4. Okay, briefly describe how you would show that the light reflected from the windscreen of a car is partially plane polarized. Okay, so when we view the reflected light through a piece of polaroid, okay, we can detect whether the light is plane polarized, is partially plane polarized. Okay, so and we can rotate the polaroid about the line of vision, and it will change from minimum to maximum and then minimum again. So by using this method, we can know that the light that is reflected from the windscreen of a car is partially plane polarized. Okay, so this is how to diagram to help you imagine. So this is the example of the windscreen of a car. Uh, so we use a Polaroid in the second diagram. So we see the clearer view, okay, clearer view compared to the first one. So the first diagram observing the reflected light without Polaroid, but the second one viewing the reflected light using Polaroid. Okay, so in the 2D diagram like this, okay, example here, this is the unpolarized light through the reflecting surface like the windscreen of the car, and then it is reflected and then pass through the polarizer here, and we can rotate this polarizer so that the intensity of the light transmitted varies from minimum to maximum and then minimum again. Okay, now we go to question next question in part 2. Okay, next we are going to discuss tutorial 16, topic waveguides, okay, part 2. Okay, the first question in part 2, state the condition for total internal reflection. So the condition for total internal reflection, light from optical denser medium to a less dense medium. So the light must pass through from the optical denser medium to the less dense medium using the symbol N for refractive index. N1 must larger than N2. Okay, next condition is angle of incident must be greater than the critical angle. So using a symbol, so theta 1 larger than theta C for the critical angle. Okay, refer to the diagram here. So this is the first medium where the light pass through. First it is incident to the interface between these two medium, and one, the medium 2 has N2 refractive index. So the theta change to until becomes theta C, where the angle of refractions become 90 degrees. So at this point is where it start for total internal reflection to occur. So that's the second condition for the total internal reflection to occur. Theta 1 larger than theta C, the critical angle. Okay, you can see the animation here. Example of critical angle is 40. You can see here 49. Okay, 49. This is the critical angle for this situation. This system for N1 larger. This is example for N water and 2 N air. Okay, next we go to question 2. Explain the principal use in fiber optics for the transmission of light. Okay, the principal use is first, the refractive index of the core is larger than the refractive index of the cladding, and then the light incident at the core cladding interface at angle of incident must be greater than the critical angle experience, and they will experience total internal reflection in this if larger than theta C. Theta, example here theta 1. So if the theta 1 larger than theta C, so after that happen, it will experience a total internal reflection. So this is the two dimension of fiber optic. So the middle is the core and then cladding of the fiber optic. Okay, you can see the animation here. After critical angle, it will experience the total internal reflection. Okay, next we go to question B. State 3 advantages fiber optic cables have over copper cables for internet communications. Okay, so the advantages is attenuation greatly reduced. Second, no electromagnetic interference. And the third, greater carrying capacity. Okay, so that's the three advantages fiber optic cables using copper cables. Using fiber optic cables compare of using copper cables. Okay, next we go to question 3. The refractive indices of the core and cladding of a fiber are 1.60 and 1.58 respectively. At what angles would total internal reflection occur at the interface? Okay, so we are going to find the uh, angles that would total internal reflection occur at the interface here, the interface of core cladding, okay, core and cladding. So that's mean here. So N1 is given 1.60 and the cladding is 1.58. N2 named as N2. Okay, so we are going to find theta C, critical angle. So for the total internal reflection to occur, this theta 1 must be larger than theta C. So we use the second derivation of Snell's law. N1 sine theta 1 equals to N2 sine theta 2. So N1 will be the core 1.60 sine theta C. So theta 1 reach theta C here. So we use theta 1 substitute into theta C into theta 1. So N2 is 1.58 sine 90 degrees. Okay, so we get critical angle 81 degrees. Okay, that's the answer. And for the total internal reflection to occur, so the theta 1 must larger than 81 degrees. Okay, next question 4. What are waveguides? And then give 2 advantages of using waveguides. So a waveguide is a structure that guides waves, restricting the three-dimensional propagation of a wave to a single dimension. Okay, advantages: low attenuation, then no electromagnetic interference. Example here, the square waveguide. We have many types of waveguide. Can be circle, square, depends on the used. So EM fields, electromagnetic fields are confined in the space, okay, available. So within the walls of the waveguide. Hence, electromagnetic wave fields are shielded from outside, and hence they have good amount of immunity against any radio frequency RF interference from outside. Okay, next. Okay, so we've done the tutorial 16 part 2. Okay, and see you in the next